will be next 45 minutes. I will be talking about vertical distribution of clouds. Yeah, vertical distribution of clouds over the Indian Monsoon Region. So I will be basically talking about only observational aspects. I will not be talking about any modeling aspects. And so this is, I will be showing a lot of results which I did along with collaborators like Professor J. Srinivasan. These are my students and from different institutes. And outline of the presentation, I will be talking basically the first vertical distribution of clouds over the monsoon region. Basically, I will be showing some results from cloud set data and in terms of mean and intra-seasonal variations. And in the tropics, you know that convection and SST relationship is very important topic of research. And so I will be talking about vertical distribution of clouds with SSTs. We have a lot of good results on convection and in terms of OLR or rainfall along with SST relationship. But today what I am going to talk is vertical distribution of clouds with SST. And also I will be talking a little bit on cloud radiative pulsing. And again it will be I will be talking about the vertical profile of clouds with the cloud radiative pulsing. So these are my outline of the present talk. So these are the data sets we have used for this presentation. ISSP data, basically the cloud climatology, cloud data, the MoES cloud data, series radiative fluxes at the top of the atmosphere, and the cloud set. I used only cloud water content. I did not use anything else from the cloud set data, even though we have data from cloud set on cloud frequency, cloud amount, but I used the basic variable like cloud water content, and the ERB top of atmosphere radiative fluxes, and SRB surface radiative fluxes, which is basically derived from a radiative transfer model, and using ISSP clouds as boundary conditions. So I will be talking a little bit on radiative fluxes, and of course for a gridded SST for SST data. And importance of clouds, as you know that clouds cover about 2/3 of the globe, so it's a very important component of the Earth system, its climate system, and they also modulate Earth's radiative balance and thus global hydrological cycle, because it affects not only the radiative balance at the top of the atmosphere, it even affects the surface radiative budget, so it is also part of the surface global hydrological cycle. And clouds as an average over the whole globe has a cooling effect of -17 watts per meter square, 30 watts per meter square from long wave, which is a positive, and 47 watts per meter square from short wave, which is a cooling. If you add it together, you get a -17 watts per meter square, which is the latest revised estimate. Earlier it was about -15. The latest estimate is -17 watts. But as all of you know that the representation of cloud process in climate model has been recognized as for decades together as a continuing source of much of the uncertainty associated with the future climate projection, especially IPCC model if you see. And I will show some results saying that the cloud process is basically one of the largest uncertainty in the climate change projections. And so the typical, these are taken from a IPCC report diagram, which shows that in a typical day you can have different kinds of clouds. So this is basically from East Pacific. You can, this is a cloud system associated with a frontal system, and also you can, there's an ITC set moving here, and if you take a cross section from here to here, you will get this kind of cloud pattern, and if you take a cloud cross section from here to here, you will get a different. So you can have at a given time, you can have globe, you can have different kinds of clouds and different properties. It's a very highly complex system. And this is the point I was making about the climate change projections. So this is taken a report from a review paper by Stephens in 2005. What I have shown here is it's a two carbon. When you double carbon dioxide, what is the sensitivity, temperature sensitivity, and of different models, different IPCC models. And you can see that the model sensitivity is not same. Some models are showing only 2 degree sensitivity, some models are showing 4. So what it makes difference between these two is basically because of the clouds. And this model is basically NCAR CM2 model is showing a larger increase in the low cloud amount. Whereas with the same boundary conditions of same carbon dioxide greenhouse gases, this model is showing a decrease in low cloud amount, which ultimately increase to larger sensitivity. So increase in temperature. So there's a lot of uncertainty among the models in the cloud distribution and the future projections, which will ultimately enter into that sensitivity. So the temperature projections from different models, the cloud sensitivity or cloud process is one of the largest uncertainty to that. And so we need observations. So historically we had surface observations where over the land we had synoptic observations. People observers look at the sky and manually they take observation, but they're very valuable observations. Over the seas we had ship observations. So we have recently a climatology has come out from Warren et al. Which they merged all the ship observations plus land observations. So this is a December, January, February, May. You can have large amount of clouds over this region and also over the stratosphere. And this is the seasonal cycle this is the zonal mean from 90 degrees south to 90 degrees north. This is for the December, January, February. This is for JJ. So they have separated between ocean and land. So this type of data are available. So we know what kind of cloud observations are. So, but again, it is a one value, the total cloud amount. And the surface observation has a bias because if a lot of low clouds are there, the observer will not be able to see the high clouds. So there is a systematic bias in the observations. And then came the satellite observations of the cloud. This is the first observation. First kind of thing is this ISCCP. It's basically a WCRP initiative of WMO, and it is from 1983 to 2008. They have brought out this data, and this is basically based on the geostationary satellites, both from shortwave and longwave fluxes they taken, and they have developed algorithm to calculate the cloud amount, cloud frequency, cloud optical depth, so and so. And you can see there's a small breakup here, this discontinuity, because not much Indian data has gone into the system. Even though we had INSAT system, so in this project, no Indian data has gone, except for 1 year, 1988, INSAT data has gone. So when we use this model, ISSP data, we have to be careful, especially on the western side of the Indian Ocean. And also, now people say that this data is, even though it's a huge data, but not recommended for climate change studies because biases can come due to satellite drifts. So I used this data for a long time back and calculated the frequency of deep convection. Frequency of deep convection, the cloud top exceeding above the 440 hectopascal, and optical depth is more than 10. So that's the frequency of we call deep convection, and what's the frequency of deep convection for 4 different months. And you can see that among the Asian monsoon region, the Bay of Bengal is the region where you get maximum deep convection. Very large amount, June, July, August, and September. And you can see that even in the July and September, we have another center of maxima over the East Equatorial Ocean. So any convection here also is also very important here. And in a year like in August 1988, when we had a good monsoon, this is the frequency of deep convection, and 1987 was a very severe drought on the month of August 87. So if you subtract this August 88 from August 87, we get this kind of anomaly pictures. What we see is here frequency of deep convection is very strong, positive along the equator, and of course this is obvious because monsoon was very bad. But what you can see is the very coherent pictures over not only over Indian monsoon region, also from the West Pacific. But frequency of deep convection was more over the Equatorial Indian Ocean as well as for Northwest Pacific. So this data were useful for this kind of inferences. So this ISSP data is a really useful data set. Then came MoES data, and then came MoES data. They also have some climatology. This is basically a high cloud amount, different types of high cloud amount, January, April, July, and October. You can see in July month, you can see the maximum over Asian monsoon region. Then I was talking about the cloud radiative feedback. This is a diagram I taken from the IPCC report. What it is shown here is the results from Selinga in 2012, and this is the total cloud radiative feedback number. It's a positive feedback, but you can see these all dots are from different models. These are from different models, and you can see there is a large spread of the model and the cloud radiative feedback. And if you divide it into long wave and short wave, also the long wave is shown as red, and short wave is blue. You can see the large spread in the cloud radiative feedback. If it is total cloud feedback, you can divide into contributions from different types of clouds like high cloud, medium clouds, and low clouds, and these are the contributions. And you can see that it's very sensitive to which type of clouds this is. Okay, so what we need to understand is which you need to really not only the total amount or cloud frequency. What we need to understand is the cloud distribution, especially on vertical direction. The vertical distribution of the cloud amount, cloud frequency is more important. And also you can calculate cloud radiative feedback in terms of amount, height, and opacity, or optical depth. You can see that there's a lot of variation from here. And what we find is the cloud radiative feedback is also sensitive to different criteria like height and opacity also. So this means that we need to find out the vertical profile. We need to understand the vertical profile of clouds. So based on that, to address this problem, CloudSat satellite was launched in April 2006. And there's a review paper in Stephens et al. By 2002 in BAMS. Basically, it's a 705 kilometer altitude sun-synchronous polar orbiting satellite. And so this is the first kind of a 3 millimeter cloud precipitation radar of 94 gigahertz. And it has a footprint resolution of 2.6 kilometer by 1 point, very good resolution, footprint resolution. But the serious problem is the CloudSat have a repeat period of 16 days. For a very, very longer data repeat period. So which is not, which sometimes it gives the problem of doing work with the satellite, the CloudSat data. So we cannot take one sample and do a lot of analysis. We need to aggregate a lot of CloudSat data to calculate some kind of means. So when you use CloudSat data, you have to be very these are first kind of results based on CloudSat observations. As I told that using CloudSat observation, we can get cloud base and cloud top. So this is a paper from METEOROLOGY et al. What this is showing is a global distribution of clouds with the base below 3 kilometer and the base between 5 and 10 kilometer and base more than 10 kilometer. So basically these are cirrus clouds. And where the cloud's top reaches more than 10 kilometers are deep convective clouds as well as cirrus clouds are shown here. So this is the first kind of observations we had from CloudSat. And so now we made an analysis of CloudSat data over the Indian Monsoon Region. But we used this data from JJS to 2006 to 2004, 5 years period, and we did analysis of mean and active and break spells. To see active and break spell, we considered to see how the cloud distribution, vertical distribution of cloud changes between active spell and the break spell, monsoon spell. So that's what we wanted to see. And before about the mean analysis and active break cycle analysis of CloudSat data, we need to understand the mean climatological pattern over the monsoon season. As we know that June to September monsoon season, we have large scale convection taking place here, as also along the west coast of India and also some parts of northeast India. So this is the mean OLR pattern, and this is the typical wind circulation at 850 millibar. We have strong Somali current, and we have strong horizontal shear from the wind here. So a lot of positive vorticity here as well as here, and so these are the basic background material which we need to keep in mind. And so as I told that we have only 16 days of repeating time at all grid points. You may not have a lot of observation. So before we start talking about the composites, and so we should know how much data has gone into analysis. So this is a typical 2 by 2 degree grid space for active spells. If I take all the composites of active spells, which I am going to show here, so this is the data which varies from almost 200 to 2000 grid points. So it's a lot of, it's not a uniformly distributed. So while interpreting the results, we have to be careful. We go back and see how much observation has gone into the things. So it's that's a tricky issue in the CloudSat data. And this is the spatial pattern of long-term mean for 5 years mean of column vertically integrated optical depth. And so what you can see is that the maximum over the east coast of Bay of Bengal and also the China region and west coast of India. And this is the cloud liquid water path. And that's also very strong along the west coast of India and also over northeast India. And this is the ice water path. This is basically because of the high clouds. And there's also maximum over Bay of Bengal and also parts of northeast India, and this is the mean effective radii. So what you can see is that where you had large low OLR and large convections, we have a lot of cloud ice water path as well as the liquid water path here. The maximum also seen here. And if you see, so what we did is we took 4 regions. One, we took it along the monsoon trough across this way, and also along the equator. And we took another north-south section, cross-section, one along the west coast and one along the Bay of Bengal. So there are 4 cross-sections which I will be showing the results. And this is the cross-section 18 to 25. Basically, it is the monsoon trough region extending from 65 degree east to 100 degree east. And this is the mean pattern of vertical extent of liquid water content. And what you can see that is the high cloud amount, high liquid water content, especially over western parts of India, western trough, monsoon trough, and also the eastern Bay of Bengal here. And this is for 10 degrees south to 10 degree north mean. And also you can see especially the western parts, you have large liquid water content. It's a mean pattern. And this is from along the west coast. This is along the west coast cross section, from minus 10 degree to plus 35 degrees north. And what you can see is also this is the same amount of large amount of cloud liquid water content over the equatorial Indian Ocean, and also along the west coast of India. And what we are seeing here is cloud liquid water content is not very strong over west coast India when compared to North Bay of Bengal. And yeah. This is a mean. This is a mean. Yeah. Yeah, sample of the years and number of. Yes. Yes, that's true. This is the cloud liquid water content. Cloud liquid water. If cloud goes there, we have rain there. It's not precipitate water. What I am showing is not precipitate water content. What I am showing here is not precipitate water content. What I am showing is a cloud. But this is the mean pattern for 5 years, sir. Okay, and this is the ice water content. This is from along the equator region. Along the monsoon trough region, and this is over the equatorial Indian Ocean, and this is along the the west coast of India, and also along this monsoon. So this is across the Bay of Bengal cross section. So this is the ice water content. So now I will show the ISO pattern, especially with the differences between active and break cycle. Before I show my results, I'll be happy to show them the results from Jeong et al. So basically, Walliser and Jeong here, they published a paper on climate dynamics. So they they try to identify the monsoon ISOs from cloud side data using, of course, they have their own ISO definition based on EOF of trim rainfall, and they identified 10 strong ISO events, and they made composites of anomalies of cloud liquid water content, and this is the 0, and this is after 5 days, 10 days, 15 days, 20 days, this is minus 5 days, how it spreads. Yeah, this is over the Bay of Bengal. This is over the Bay of Bengal cross section, and what they are showing, and below what they are showing is the rainfall anomalies. So green is above normal rainfall, and blue is below normal. So the 0 corresponds to, you can see that a lot of rainfall over the equator, so which corresponds to our typical break. Okay, so this is what their 0 is equivalent to our break monsoon condition, and what you can see is here is a positive cloud liquid water content over the equator, and negative cloud liquid water content over here, which also moves with the time. You can see that positive liquid water content moves with time, northward propagation is seen. And what also they are also highlighting is that this shift in the, or tilt in the vertical. You can see that from here, there's a tilt here, and also is a tilt here, tilt here. So they say that this is one of the mechanisms. Of course, I am not an ISO specialist, but the people say this tilt in the cloud liquid water content is one of the gradients for explaining the northward propagation of ISO. Cloud side. Okay, and so this is the typical ISO pattern, and if you really see that from the cloud ice water content, and this looks over here, the northward tilt is not really seen. The tilt is not seen; it's all vertical profile, and here also this kind of northward propagation of positive anomalies are observed here. So when the rainfall comes here, this is corresponds to an active condition, and also is seen here positive anomaly. So what they explain is with the cloud side data they are able to explain the ISO pattern in the monsoon convection, and also they are talking about the southward tilt in the vertical of the cloud anomalies, cloud liquid water content anomalies. The composites of 10 events. Composites of 10 events. Composite of 10 anomalies. So the mean is from the whole 122 days. They subtracted from yes. So we also did the similar kind, but we did not see that propagation. We did not see. We just took the composites for different active spells and the break spells, and so we see when during active spells, if you composite the mean OLR anomaly, you get negative anomaly here, and you get a positive anomaly here, which shows that a lot of convection here. But convection is suppressed over northeast India, and also especially in the east equatorial Indian Ocean, which is important. So when you interpret our results, which I am going to show next, these results are very useful. During a break, what you can see is that it is suppressed monsoon convection whole India as well as towards West Pacific, whereas the convection is enhanced over the equatorial Indian Ocean, especially over the east equatorial Indian Ocean, and also over northeast India. So I will show some few results of active and break spells between using cloud side data. So this is over the equatorial Indian Ocean. You can during an active, you can see that all are negative. That means the convection is completely suppressed over the equatorial Indian Ocean, whereas and this is for the monsoon trough region, 18 degree north to 25 degree north active. And this is the anomaly of what we can see is not completely, the monsoon trough is not completely covered by positive anomalies. And because it's basically the synoptic scale. What you can see the anomalies in the synoptic scale. You can see the positive anomalies over Bay of Bengal, then also in the western parts of the monsoon trough region. And also if you see the 10 degrees south in the during break, what you can see is the enhanced, here is very clearly it is coming. East equatorial Indian Ocean is enhanced liquid water content during a break, and whereas in the monsoon trough region, what you can see very interesting results here is during monsoon trough, during break, what happens in the monsoon trough moves north, and so northeast India gets a lot of rain, and that is very clearly seen here east of 90 degree, and because I average up to 25 degree north, so some kind of signal northeast India rainfall, excess rainfall over here. But over the monsoon trough region, you can see that there are positive anomalies, but it's very shallow. So, which is very typical of representing the heat low type of circulation over the monsoon trough region. When monsoon break happens over the monsoon trough region, we will still have clouds, but clouds are very shallow because the circulation is a very shallow circulation, return circulation. Whereas in the active condition, it's a very deep moist ascent. Whereas in the break condition, we have a very small shallow ascent. So I will show later. I will show you a MoES result which show that there is, if you take the total cloud frequency, there's not much difference between active and break. If you see that from the top of the cloud amount is same between active and break spell. What makes between active and break spells is the amount of convective deep clouds, not the total amount of clouds. Still you have a lot of clouds over Indian monsoon region during a break, as which I presented recently in Pune, and some foreigner asked me, so can I get a sunshine during a break? Yeah, because I showed even break we will have all cloudy days. Yeah, these are all long breaks. I told it is possible you have to wait because we are not able to predict it properly. Yeah, so the cloud set results are very consistent with our knowledge that heat low type of circulation exists.
You have a statistics on the south.
Yes, sir. Yeah. not from CloudSat, but from ISSP data we have, frequency of deep clouds. Yeah, I have that. And this is again along the west coast of India, 70 to 75 between active. What we can see, the over equatorial Indian Ocean convection is suppressed for us. So you can see that there is a lot of convection over along the west coast of India during an active spell, which is very clearly seen. And during a break, you can see the whole west coast is suppressed of convection, large scale convection, so a lot of negative anomalies. And in the monsoon trough region, you can see that this is 85 to this is a Bay of Bengal cross section. You can see North Bay of Bengal is positive cloud water content, and also this is the break. And break also you can see this is the break condition during between 85 and 90 degrees east. It's the Bay of Bengal cross section. And during break, what you can see that your equatorial Indian Ocean, there is a large scale positive cloud liquid water content, which basically says that equatorial Indian Ocean ITC set is very strong. So this CloudSat, the vertical profile of CloudSat data has given us some idea about how, and this is same thing, but it is of ice water content, the same results, so the results are almost same. And so if you average over Bay of Bengal, take an area weighted average and between active and break spell, and active is so much increase during active spell, we can expect from liquid water content, and this is ice water path. So both are between a break and active spell, there is a large difference over Bay of Bengal. Okay, so this is the MoES results which we have done it between same kind of active and break spells which we defined, and the top one shows the total cloud amount. You can see that this is the active, this three panel is basically active spell, this is the break spell, and this is the difference between active and break spell. What we can see is that you can see the number figure, there are hardly any differences between the total cloud amount between active and break spell. We get same kinds of clouds. But what you get is basically this is the cloud optical depth, the active, and this is the break. The large difference of a cloud optical depth between active and the break. So what during active what we get is the deep convective clouds during active spells. And this is the cloud top pressure. You can see the cloud pressure is very deep clouds, whereas here the cloud top pressure is not very high. So what? How do you calculate the total cloud amount? This is the cloud amount. This is a MoES algorithm. I am not. I don't know. Yeah. Yeah. 1 year or how many years? Maybe about 3-4 years. Yeah, I will. 7 years. I will go to the next topic on SST and convection relationship, which is also a very hot topic, as we know that this is the first paper we had it in Nature, Godgill et al. 1984. 1984 just came out from college after my MS. So she wrote a paper in Nature, basically relating SST and cloud intensity over the monsoon region, Indian monsoon region, which shows that there is an increase in large scale convective clouds after 27.5 or so threshold, the SST threshold. So this is the first kind of results which we had in India, and it's a 27.5 threshold. Is the threshold SST threshold for deep convection?
Cloudiness intensity from Sadler data. Okay.
Yeah.
The first data, Sadler had made it into
At that time, we did not have OLR and all.
Intensity was calculated using some threshold as something about 6%. Okay.
So basically, it's a cloud data. It's basically satellite data. It's a cloud intensity, cloud amount from the satellite data. And at that time, OLR was not there. But of course, she has done with the OLR later. This is the OLR picture. Same kind of inference we can get is a relation between SST and OLR. You can see that the strong threshold about 27.5. Afterwards, the strong convection starts, and deep increase in OLR, a lower value of OLR, which basically says that the deep convection starts. And also there is a famous paper by Lau et al. Which shows that this relationship is not uniformly true, and there are differences in the relationship, and that depends upon the atmospheric circulation conditions. So the convection is not really triggered by only SST condition, but also atmospheric dynamics plays an important role. So they divided the whole tropics into different zones depending upon the mean vertical velocity, and they divided into different zones, and they found out the relationship is slightly different from different regions. So when we talk about convection, especially over the Indian monsoon region, SST is not the only threshold which can trigger the convection. Atmosphere also should be dynamic and should be allowing convection to take place. And we did, and this is a very famous paper recently which says that the SST thresholds are increasing with the time. And in future, they say that in future climate, the SST thresholds are going to increase, not 27.5. With the warmer climate, we can expect little more better, higher threshold to come for convection to take place. So in this context, we did an analysis. What we did is, using cloud site data, we did an analysis of thresholds of, so what we want to know is how these SST thresholds are related to the vertical profile of cloud liquid water content. Whether it is there in a relationship between SST and the vertical profile of cloud liquid water content. That's what we wanted to see. And not a one parameter like OLR. So this is a kind of a binned the analysis for the whole tropics 0 to 360 and 30 degrees south to 30 degrees north. Only the black is for cloud liquid water content and red is for cloud ice water content. What you can see is, and you have you convection starts somewhere at 27.5. This is for the whole tropics, and even if you take the North Indian Ocean between 30 degrees to 100 degrees east, and 30 to 40 degrees north, also you get a similar kind of relationship. So this is the vertically integrated cloud liquid water content and cloud ice water content. So if you really see, so I will show the next one. Yeah, this I am not sure. This dip I am not sure what is really happening.
That is also
Yeah. Yeah, this of course, these are OLR also. If you plot, you get after 31 the OLR comes down. OLR convection comes down.
That is because the clearest sky overlie the warmest sea.
Okay. Okay. Yeah.
It is true that you are more prone to get clouds if you have about the threshold, but
Yeah.
there is a large variation.
Yeah.
But highest SST you get only under clear sky.
Yeah.
That is what the difference is.
Yeah. 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 Okay. And this is of course we took only North Indian Ocean 0 to 25 degree north and 30 to 100 degree east, and you can see that beautiful increase in cloud liquid water content as also kite ice water content after 26. So it is around 27.5. So Sulochana's the threshold still remains 27.5. Okay. And now this is the vertical profile of SST. This is again for the whole tropics. The what below shown is the cloud liquid water content, and above what I shown is the cloud ice water content. What we are seeing here, this may be associated with the stratus cloud, marine stratus clouds, with the lower SSTs, especially over the East Pacific Ocean. And so when here, if you go in this range, 27 to 30, what you can see that the suddenly increases, cloud liquid water content increases after 27.5, and also the ice water content sharply increases. So this is a vertical, this is the first kind of information, at least I know, is SST with the vertical variation of cloud liquid water content. And if you take only for Bay of Bengal, North Bay of Bengal, very sharp increase. Of course, the diagram is not very clearly drawn, but you can see that there is sharp increase after 27.5, and the most noticed increase is seen over the ice, over this region, basically this ice water content. So this is the vertical variation of cloud with the SSTs. So the question is whether this kind of variations are really seen or simulated by the models. That's what the next question we have to answer. So these are a good observation which we can make use to analyze the model response of SST and convection. This is scatter points with different levels. But this is again the same kind of relationship. So this is the SST and this is the cloud liquid water content at different layers. The layer 1 is basically 0 to 3 kilometer. Layer 2 is to 3 to 6, and this is 6 to 9, 9 to 12, 12 to 15, so and so. So what we can see is the sharp rise, but especially seen from 3 to 6 kilometer. So what we can see is it is really flat here, but you can see sharp rise of around 27.5. This is for Bay of Bengal. This is for Bay of Bengal, and you can see that this is seen at all levels. Seen at all levels. So this hockey stick kind of information is also replicated in. So how many minutes I have?
5 more minutes because of our interruption.
Okay. I'll speak a little. I'll talk about the cloud radiative forcing, and as we know that cloud radiative forcing is a concept in which we describe the radiative effects of clouds, and you know the clouds have both the effects from short wave as well as long wave. Short wave we have a cooling effect, globally I'm talking, and long wave has a positive effect, is a warming effect, and so we can calculate this cloud radiative forcing if you know the clear sky flux as well as the cloudy flux. You can subtract from clear sky flux and cloudy flux. So this is the short wave flux cloud radiative forcing. This is long wave cloud radiative forcing. So we did there was a paper by Keel in around later 90s saying that over the equatorial Indian Pacific Ocean, especially warm pooled region, West Pacific, the short wave forcing and long wave forcing gets cancelled. But both are the same amount but in the opposite side, so gets cancelled. So the net radiative forcing is 0 over the warm pooled region where the convection is very strong. But accidentally when we did the analysis, we did not find over the monsoon region. Over the monsoon region, we find a very different pattern of cloud radiative forcing. So paper I wrote with Professor Srinivasan in 2000, published in Journal of Climate. But when we did cloud radiative forcing, this is based on ERB results, Earth Radiative Budget results, 1984 to 89. And when we did the analysis, we found large negative net radiative forcing of our exceeding even 30 watts per meter square over Bay of Bengal, North Bay of Bengal. So if you really plot long wave scatter plot over Bay of Bengal between long wave forcing and short wave forcing, what we are seeing is, you can see that it should go along this line, but what we are seeing here is, especially over the ocean point, there are points where it goes up 45-degree line, and which shows that at the given long wave forcing, short wave forcing is much stronger. So giving the net radiative forcing is very large negative forcing, which is first time we reported, and then we try to find out what is the reason could be. And what we found here is you can see optical depth of high clouds. You can see that over the West Pacific, where Dr. Keel was suggesting that there's basically the net effective is 0, because if you see the high clouds here, large high clouds are seen only over Bay of Bengal, not over Pacific, West Pacific. If we over the whole monsoon and West Pacific region, where Bay of Bengal is and close to China region is the region where you have large optical depth clouds, high clouds with large optical depth. And if you really plot the optical depth along the radiative forcing, what we are seeing is it is small increase here in this is for short wave, this is for long wave. What we are seeing here is after around 10 or so, long wave forcing gets flattened, whereas short wave still rises. Okay, so at large optical depth, the short wave forcing far exceeds the long wave forcing, which causes the large net radiative forcing. So we've attributed this asymmetry in the long wave and the short wave forcing due to larger amount of deep convective clouds over the monsoon region, which is not seen in the West Pacific region. And then Satyamurthy told that is because of the strong easterly jet. The high clouds, why we get it over Bay of Bengal is because of the strong easterly jet. Okay, fine. And this is also seen over the surface radiative forcing. If you really calculate using a radiative transfer model, put ISSP clouds there and calculate the radiative forcing in the surface, we so they just a plot a scatter graph, they get a good correlation, and they okay, so what I'm just as a side by I told that aspect, but I agree with you. And so this strong asymmetry in the radiative forcing is seen even in the surface, and surface radiative asymmetries can be even more. Even net radiative forcing can be even hundreds watts per meter square. So large cooling by the monsoon clouds over the monsoon trough region, or Bay of Bengal, which is very important for the hydrological cycle. So when we talk about whether models simulate this kind of asymmetry, the answer is no. I don't have immediate results to show, but I've seen a couple of model results which shows that models are not able to reproduce this large asymmetry over Bay of Bengal. So their model basically cancel each other, long wave and short wave cancellation. I have some more results from, so if you really take the latest series data, also this asymmetry is clearly seen. So this is a very established concept that net radiative forcing over monsoon region is large negative. And with the cloud side data, we try to estimate it why it is because of different layers of clouds. And I will not go in detail, but I basically see that this is basically because of the cloud liquid water content.